So where are we? We've gotten to this stage where we have the small increments formula. And the small increments formula gives us the change in value of the function as a linear combination of the changes in value of the variables that the function depends on. This is where we have f as a function of n variables x1 up to xn. And the coefficients in this linear combination are the corresponding, the appropriate partial derivatives of the function with respect to the ith variable. Okay. So you're adding up these products, the evaluation of the partial derivative at the original point multiplied by the change in value of the ith variable. Excuse me, this isn't an equation, this is an approximation to the change in value of the equation. So that's what we have. That's our one of our main tools that we've developed so far. We're now going to look at another application to this. Okay, so this is section 1.8, which is the chain rule and Jacobians. So the first thing we want to do is just recall the thing we already know, which is the chain rule for single variable functions. Okay. For the single variable case, okay, we may have a functional relationship y equals f of x between two variables, so y and x, and in some situations, the variable x that y depends on through f may in fact be a function of another variable t. Okay. So you get this familiar picture that y is f of x, but x is in turn g of t. And everybody knows how to obtain the derivative dy dt. You do it using the chain rule that you have for single variable functions. So you differentiate the outer function first of all, which would be the derivative df dx, and then you multiply that by the derivative of the inner function, which is your g of t function. So this would be multiplied by dg dt. Or indeed, you might express that as what is the derivative of y with respect to x, this first one, y is equal to f of x, so the derivative of f with respect to x is dy dx, and the derivative of g with respect to dt, another name for that is dx dt, because x, as it depends on t, is given by the function g. So everybody knows, should all be familiar with this. This is the chain rule for functions of a single variable. Okay. So that's all well and good. That's what we know and are well used to using. But what we want to explore now is what happens when the function is multivariable. Okay. But what happens, or what's the situation when your y is a function of more than one variable? Okay, so when y is a function of n variables x1 through xn, so i.e. f is a function from Rn to R. It's a real valued function from the n-dimensional Euclidean space to the real numbers. But we might also have another basis or another set of coordinates z1 up to zn for Rn. Now we'll see some concrete examples of different coordinate systems for different spaces soon, but just to speak abstractly, suppose we've got some system of coordinates x1 to xn for the n-dimensional space, But we may also have another competing set of coordinates or another alternative set of coordinates. And the question is how to find the partial derivative dy with respect to one of these new coordinates zi. So this is the question we're facing. Does it, and how exactly, does it depend on the derivatives of y with respect to some of the xj variables and the derivative of, say, some of the xj variables with some of the z, with the zk's? Now there's a proliferation of subscripts here, just indicate all the available partial derivatives, the derivative of y with respect to the original x's, and the derivatives of these x's with respect to the zk. And this would be the situation when the variables xj may be given by some functional relationship uj to all these new coordinates. Okay, so there's a large kind of question there is how do all these things fit together? How do we express and think about the derivative of our quantity y with respect to one of the new coordinates? How do we think of that with respect to the coordinates xi that we already have? And if these old coordinates xi are linked to the new set of coordinates through a series of transformation functions, so that u would be a transformation function. How can we put all these parts together to find nice expressions for the new partial derivatives? Okay. So that question is more or less laid out in that first half of page 13 there, the notes. So before we get into that, just to maybe look at one concrete example of what we're kind of meaning. So this is example 1.9 from the notes, and that is the polar coordinate system in R2. Now this is something which you may well be familiar with, seen it in other areas, but we're well used to thinking of R2 as being the system with coordinates x and y. Okay. Or let's call this capital X and capital Y axis. And any particular point will have its x coordinate and its y coordinate. With those two numbers, you can locate a particular point. Well, that's a very kind of blocky, Cartesian, Minecrafty way of locating the position of something in the plane. We can do this in other ways as well. One very natural way to think about the position of something is to give its distance from a fixed point. Okay, so we can have, normally there's a special point in the plane, which is called the origin, and we might give r the radial distance. Call this point P, the radial distance of P from the origin. That's a very nice, meaningful measure of the location of a point. Of course, all it does is pin down the point P to a whole circle's worth of points, because they all have the same radial distance from the origin. So to fully pin the point P down, we can also give the measure of this angle here, theta. Okay, so theta is called the polar angle. Polar angle for the point P. Okay? The angle that the radial line, that the radius line makes with the positive sense of the x-axis. Okay? So the pair of values x, y are the Cartesian coordinates of the point P. Cartesian should be capitalized. It's named after Descartes, French philosopher. Mathematician. I mean, they were all the same back then, really. And r and theta are called the polar coordinates. Okay. And for some situations, the polar coordinates are more appropriate for locating points in the plane. For other situations, the Cartesian coordinates are most appropriate. If you're tracking the movement of some object in the plane and the movement is in any way circular, then it's probably going to have a much simpler description in terms of the polar coordinates. Okay? The polar coordinates are naturally adapted to talking about the location of things on circles. Okay? Because the information is very circular. Okay? So, well, what's the relationship between these two? Well, there's a very clear functional relationship that you can write down between these two systems of coordinates, and you can extract it from the right angle triangle that's formed here, with the radius line r as the hypotenuse, and the x and y coordinates give you the lengths of the adjacent and opposite sides to the angle theta. Okay? So these things are linked by the quantity, by the functions x equals r cosine theta and y equals r sine theta. Okay? To some degree, you'll be familiar with these things already. Okay? So if you like, this could be x as a function u of r and theta, and this could be y as a function v of r and theta. So this up here, when I was indicating that the old coordinates xj might be some transformation functions of the new coordinates, well, here's a concrete example of that, where the previous x coordinate is given by this nice function u of the two new coordinates, and the previous coordinate y, the second Cartesian coordinate, is given by this nice function r times sine theta of the new coordinates, of the polar coordinates. So the question now becomes, if we have some quantity, I won't call it y, we'll call it z. If we have some quantity z which is given as a function of x and y, what does the partial derivatives dz dr and dz d theta, or what do these things look like? Okay. Or how might they relate to the other partial derivatives of the function f, df dx and df dy, and the partial derivatives of the transformation equations, du dr, du d theta, dv dr, and dv d theta. So in order to answer this question, just like in the single variable case, we need the chain rule for multivariable situation. Okay. And And to develop the chain rule, we use the small increments formula. Okay? So just to go back to just away from the specific polar coordinates again, so just to generalize it a bit as I do in the notes. So we consider we have this function f of a pair of coordinates x and y. You can think of those as the Cartesian coordinates. And a new pair of coordinates, s and t. Okay. And if we know that x is some function u of s and t, and y is some function v of s and t. Okay. Specific example of those in the case of polar coordinates we've just given. But now we just kind of generalize again for this discussion. Well, if we apply the small increments formula, the small increments formula will say that the change in z is approximately df dx by the change in x plus df dy by the change in 1. Okay? Sorry, did I put that away too soon? Okay, so that's our small increments formula. Now, what we can do here is divide across by the quantity delta s. And we put it in a fraction with the delta x and the delta y. Okay, so what I'm doing there is I'm taking the quantity delta s, which is a change in the s variable, and dividing both sides of the approximation by it. And we then let delta s approach 0, converge to 0 on both sides of this. Now there's some technical details I'm skirting over about how all this convergence happens, but if you look at what's going to happen, the quantities df dx and df dy are unchanged. They're just representing the partial derivatives of f evaluated at some certain base point. Okay? But the quantity delta s is the quantity s is changing, and because x and y both depend on s, when s changes, you get associated changes, delta x and delta y, associated changes in the variables x and y. And as we let the change in s converge to 0, the left-hand side becomes the partial derivative of s with respect to z. Okay? So remember, the partial derivative of a quantity z with respect to s is just the limit of the relative change in value of the quantity z when s undergoes a change, and the other variable t is kept constant. So when you take the limit as delta s approaches 0, this quantity on the left-hand side in the limit becomes the partial derivative, dz ds. df dx is unchanged, df dy is unchanged, but the quantity delta x over delta s, in a similar way, that converges to the partial derivative dx ds. And the quantity delta y over delta s, that approaches the partial derivative dy dx. We're still adding them together. And what also happens in the limit case is that what was provided, the small increments formula provided us an approximation to the change in the quantity z. But as we said, it's a very good approximation for small values of delta x and delta y, and as delta x and delta y get smaller and smaller and smaller, the approximation gets better and better and better. So actually in the limit, this is no longer an approximation, but it is in fact an equation. And we get an equation like this, which is called one of the chain rule equations for this two variable system. Okay? So we've got a quantity z, which is a function of x and y, originally, yeah, so z is defined as a function of the old variables x and y, but there might be an alternative pair of coordinates, s and t. And this chain rule equation tells you how to think about the partial derivative of z with respect to one of the new coordinates in terms of the partial derivatives of f with respect to the old coordinates and the derivatives of the old coordinates with respect to this new coordinate s. Okay? And similarly, dividing, and I'll say star here, so I'll label that original small increments formula with an asterisk. Dividing star by delta t on both sides, taking the limits, as delta t goes to 0, I won't write in the intermediate approximation, but that will give gives the other chain rule equation for this situation. Delta z dz dt will be df dx dx dt plus df dy dy dt. That's the second chain rule equation. The second of the two chain rule equations for this two variable system. So 1 and 2 are the chain rule equations. For this system where you've got an old pair of coordinates x, y changing to a new pair of coordinates s and t. So that's consolidated in definition 1.5. Just kind of records all that and states all that cleanly. But now that's the situation for two variables. It's very tempting to see what the generalization would be to higher dimensions, okay? So not just looking at functions with domain the plane R2, but higher, R3, R4, etc. Any number of variables, okay? So that's generalized in the next definition. So in this generalization, you've got a quantity z being a function f of n variables x to n, and a new system of coordinates s1 up to sn, then you've got a whole bunch of equations, actually n different chain rule equations for this. And each equation, well, the ith one tells you what dz dsi is, and it's a combination of this expression here, where you differentiate f with respect to each of the old variables, and then multiply that by the partial derivative of xj with si. Okay. So you got the I is the index on the new variable s on both sides, and then we're summing over all of the old coordinates xj, x1 through to xn, multiplying each partial derivative df dxj, is the partial derivative of f with respect to the old variable, multiplying by the corresponding derivative of the old variable as it depends on the new variable si. Okay? And you've got one of these equations for each value of I from 1 to n. Okay, and those are the chain rule equations in the general case. These are the chain rule equations for the system xj changing to the system sj. Okay, so let's look through an example of one of these. So we'll look through example 1.10, which again returns to those polar coordinates in 2 dimensions. So we consider this expression, which is denoted by curly f, and it's x df dx plus y df dy. So this is a combination of the variables x and y and the partial derivatives df dx and df dy. So it's some kind of differential expression in terms of the old system of coordinates. So consider this, and we want to translate this from Cartesian to polar coordinates. Okay. So this is the task. So we want to find out what's the equivalent expression for curly f here. It's like a script f, an ornate script f. You see it in the notes there on page 14. Get the equivalent expression for this, but only in terms of the polar coordinates. So we take the chain rule equation. Now we want the chain rule equation that's going to tell us what to do with df dx. Chain rule equations can go both ways. They can tell you what the derivatives of f with respect to the new variables are in terms of the old, or the old in terms of the new. So here I'm applying it to the case where I want to express df dx in terms of the other coordinates. Okay. So this is going to be df d theta by d theta dx plus df dr by dr dx. So to work out these partial derivatives over here, I mean, these expressions, df d theta and df dr, are fine as they are. They can feature in the translated version of curly f, okay, because they are derivatives with respect to the new polar coordinates. But in order to get a handle on these quantities, d theta dx and dr dx, I'll need the transformation equations between the two systems, but in the other direction that I've quoted them already. Okay, so we need to know, how is r a function of x and y? Well, r is the radial distance. So the radial distance is, of course, the square root of the sum of squares. The square root of x squared plus y squared. It's the distance from the origin to the point with coordinates x and y. And the expression for theta in terms of x and y is the arctangent, the inverse tan of y over x. Okay, so these all come from this basic triangle where you've got theta, r, y, and x there. So point P is the origin down here. Okay, so extracting from that triangle, r is the square root of the sum of squares, and theta is the arctangent of y over x. So these partial derivatives, dr dx and d theta dx, well, dr dx, I can differentiate this quantity with respect to x. Remember, you treat the y variable as if it's a constant. So you have to use the single variable chain rule idea here. So you're differentiating this bracket to the power half, so it's going to be a half times the bracket. You reduce the exponent by 1, so the new exponent in the bracket is minus a half. Then I multiply by the derivative of the inner function with respect to x, so that's multiplied by 2x. And I can translate that as much as possible into polar coordinates. Well, the 2 and the half will cancel. And you've got the x at the top. And there we've got x squared plus y squared to the minus a half. So that's the same as 1 over x squared plus y squared to the half. So that's r in the denominator position. The derivative of theta with respect to x. Well, the derivative of arc tangent, see there it's in the notes on page 15, that's 1 over the argument squared plus 1. This would be 1 over y plus x all squared plus 1. And then itself multiplied by the derivative of the inner function, which is y over x with respect to x. So that would be multiplied by minus y over x squared. And doing that algebra there, see, it does simplify a little bit. Because this x squared, you can multiply that x squared there in the denominator through this denominator. So it will clear that x squared, and you'll be left with y squared plus x squared. And in the numerator, then you'll just have minus y. So that would translate into polar coordinates as much as possible. See, because x squared plus y squared there in the denominator is r squared. Okay, so we have these partial derivatives here, as simple as we can make them. dr dx is x over r. d theta dx is minus y over r squared. So we can return back to our first chain rule equation and substitute those in. So my quantity df dx will be minus y over r squared df d theta plus x over r df dr. Yes, question.
D theta over dx. Why is the minus y over x squared?
So the question about to explain all this in the d theta dx. So when we're differentiating this, okay, it's a function arctan, the inverse tangent of a non-trivial function of x. So I need to use the chain rule, the single variable chain rule. The derivative of the inverse tangent function, the arctangent, is 1 over its argument squared plus 1. That's what I see here. So this part here is the derivative of the arctangent bit. But you're applying the chain rule, so you then need to multiply by the derivative with respect to x of the inner function, which is y over x, and the derivative of that will be minus y over x squared, okay, because x is in the reciprocal position there. Is that okay? Yeah. And then just taking this x squared here in the denominator, multiplying it through that denominator gives you y squared plus x squared, which is r squared, and you're left with the minus y in the numerator. Now that's part of what we need. So this here is part of what we need. This gives us df dx in terms, as much as possible in terms of the new polar coordinates. df dx is this thing here, which features in the curly f. It's multiplied by x, of course. Similarly, we can get df dy. And well, skipping over the details, but we would need to, well, let's do it. Let's give you the intermediate chain rule equation. So the chain rule equation would be df d theta dy plus df dr dr dy. Okay, that would be the intermediate chain rule equation. And then working through the partial derivatives d theta dy dr dy, just like we did with d theta dx and dr dx, that will give us the expression x over r squared df d theta and plus y over r df dr. Or that should be curly box to go with that curly box. So those are the ingredients for evaluating or for forming the new expression for curly f. Okay. So curly f was x df dx plus y df dy. Substituting in these two quantities now that I have in these curly clouds here, give me minus xy over r squared df d theta plus x squared over r df dr, then plus xy over r squared df d theta plus y squared over r df dr. So I have x times df dx, which is the x times df dx, so x times all of that, plus y times df dy, so plus y times all of that. That gives me these two lines here. And you can see these two terms here in the left column cancel. You've got a negative and a positive. Same thing. So we're left with this expression over here. The df dr is common to both, and the 1 over r is common to both. And so we've got x squared plus y squared over r df dr. But of course, x squared plus y squared, the sum of squares is of course the square of the radius. So that's r squared over r. So the whole thing simplifies really nicely down to r df dr. Okay. So this combination, it might appear in a differential equation describing some kind of system where you're interested in the quantity f and how it's originally conceived as depending on the Cartesian coordinates x and y. But this procedure shows you how the chain rule equations can be used to translate the same quantity, but now expressed in terms of a new system of coordinates. Okay? And it does have a fair simpler structure in terms of the polar coordinates, because it's now just a single constant, single derivative df dr multiplied by its corresponding variable r. The quantity curly f this actually seems to be independent, completely independent of the angle variable theta. And it seems to only depend on information about the radius and how the function f depends on the radius. Okay. So in advance of the second session here, I've got some extra problems, which I'll hand out to you. And in the second session, we'll do a workshop session or a problem session using some of these. Okay, so we do have to move downstairs now, so we'll recommence at 5 o'clock down in D143.